First of all, welcome to today's session. I hope you're all doing fine in these challenging times. As you might have guessed, based on the title of today's symposia, today's talks will be more or less all about making sense or nonsense of thermal sensors, sensing, and integration. My name is Davide Filingeri. I come from University of Ljubljana in Slovenia, and it is a pleasure to co-host or co-organize this symposia with Chris Tyler from University of Roehampton in UK and Stephen Chung from Brock University in Canada. I would first of all really like to thank all of you for attending. As you know, we are now in in the fourth week of this weekly symposia, and we're really happy to get more or less positive feedback, and we'll obviously try to keep up the good work and keep you scientifically entertained in the future. Before we start, I would just like to share a few basic informations. I will just share my screen now, and in particular, as you know, all of the past talks that have already been conducted are being published on our webpage, ICEE2021.com, and they're also published available on YouTube. In addition, we also have student handouts which are prepared by the speakers and are aimed at providing lecturers or instructors who are running courses in environmental physiology or exercise physiology to use them during their teaching. So do feel free to use them. I would also like to mention that during the actual symposia, we really encourage you to make use of the Q&A feature in Zoom. You will see it's on the bottom of your screens normally, where you can pose your questions to the participants, to the speakers, and we will try to accommodate a few questions during the live questioning after each respective talk. But the presenters will also be able to answer you live within the Q&A feature. As I mentioned before, we have an excellent session today with three great speakers. We will start with Nicolas Ravanelli from University of Montreal in Canada. He will talk a little bit about biophysical and physiological determinants of heat dissipation. The second speaker will be Zach Schlader from University of Indiana, USA, and he will present some interactions between autonomic and behavioral responses in thermoregulation. And last but not least, our third speaker will be Davide Filingeri from University of Loughborough in UK, and he will present some recent advances in understanding human skin wetness sensing. Before we go to Nick, I would just like to mention that the next upcoming symposia on the May 14th will be focused on the first occupational topic, in particular on firefighting. We will host Emily Watkins and Anthony Walker, and most importantly, this is the first session that will be dedicated or more accommodating to our Eastern friends, in particular in Australia, Japan, and Asia, with the session taking place at 9:00 hours British Standard Time, meaning 6 p.m. Sydney, etc. You will see. We will let you know also further on Twitter about that. And also, I would like to mention we have really nice sessions coming up with pollution, some environmental preparations, also featuring an Olympian, exercise in the cold. So we'll keep them coming. So please follow our webpage. And not to take too much time from our speakers today, I will stop sharing my screen and give the mic to Nick. Here you go. The floor is yours, Nick.
Awesome. Thank you, Tade. Thank you, Chris, Stephen, and Tade again for having me today to talk. Tade, it's been a while since I've heard someone present my name so elegantly, so thank you for that. Share screen working?
Yeah.
Perfect. All right, so as Tade had mentioned, today my talk's going to be about the biophysical and physiological determinants of sweating during heat stress. And before I mess this up. Perfect. So the stuff that I'm going to present today is a bulk of work that I did during my PhD at the University of Ottawa under the direction of Ollie J. and Pascal Imbeau. And most of it was collected at Ottawa, and a portion of the data that I'll show was also collected during a 6-month abroad that I did at the University of Sydney. So traditionally, we think the relationship between sweating and core temperature to be a response where the hotter we get, the more we sweat. And this relationship has been modified by factors such as heat acclimation, circadian rhythm, skin temperature, fitness, and sex. However, more recent evidence has been brought forth, which both complements the traditional paradigm, but also satisfies the first law of thermodynamics for heat balance. And so to get to this, we'll have to first revise our understanding of what conceptual heat balance is. And principally, it's the balance between the heat that we produce and the heat that we must lose to the environment to maintain a stable core temperature. And we can conceptualize this within a longer version of this equation, and I'll break this down quite quickly. So one of the first components that we have is our net heat production. And this is the difference between our metabolic energy expenditure and our external work rate. We can lose heat through conduction, which is surface-to-surface contact. We can lose it through convection, which is the movement of fluid mediums across the surface of the solid. We can gain or lose heat through radiation. We can lose heat through our respiration. This is a combination of convective and evaporative heat loss. And lastly, we can lose heat through one of the largest modifiable pathways, which is the evaporation of sweat from our skin surface. Now, the last component in this equation is denoted as our heat storage. It is the S component. This is basically a placeholder so that if we're not able to dissipate all the heat that we're producing, or conversely, we're losing too much heat to the surrounding environment, this will be either positive or negative. And so the remaining of this presentation is going to focus exclusively on the evaporative component to this equation and how this might provide better insights into what determines our steady state sweating during compensable heat stress. And so let's take this conceptual heat balance equation again, and let's take a situation where we don't have any heat storage. This is a compensable environment. All the heat that we are producing or gaining, we're able to freely dissipate to the environment through dry and evaporative means. Let's make it simple, and let's eliminate the dry heat exchange component by having a condition where dry heat exchange is quite minimal. As such, any proportional rise in metabolic heat or in heat production should result in a concomitant rise in our evaporative requirements to attain heat balance. And so what we've been shown by Daniel Gagnon in 2013 and Jay Physiol is that with proportional rises in metabolic heat production in the same ambient condition, we see a linear rise in the whole body sweat rate as it is on the y-axis, suggesting that there may be a link between evaporative requirements for sweating and the actual physiological response of sweating. So now let's reintroduce the dry heat exchange component and reorganize our equation so that we have the evaporative requirements is effectively the net difference between our heat production and dry heat loss. And when we evaluate it in this perspective, again, we see the requirements for the evaporative heat loss show a positive relationship with our whole body steady state sweat rate. And now these ideas right now have been shown in this paper was within the whole body calorimeter, but more recent evidence has been used in environmental chambers. And so Lily Hospers, who is a graduate student of Ollie's at the University of Sydney, recently published this paper in the Medicine, Science, and Sports and Exercise, where they had a total of 140 bouts of 2-hour exercise amongst 21 participants, all data collected from the Usarium military group in the States. Ranges of ambient temperatures of 15 to 30 degrees Celsius and skin temperatures ranging from 27 to 34. And again, we see this nice linear relationship between the evaporative requirements for heat balance, or as is denoted as EREC on the x-axis on the graph on the left, with a linear relationship with whole body sweat rate. If you look at the graph on the right, this excludes the dry heat component, and we can see that if we just assume it as a function of heat production, the relationship is weaker relative to when we actually account for dry heat exchange and we look at it from EREC. Again, myself and colleagues from Radboud University tried to look at a larger sample of people, but in a more free range condition, because what's been shown right now is when we have exercise durations fixed, we see this function. But what if we now have a race, such as the Seven Hills Run, where you have people running 15 kilometers with staggered finishes? Do we see this similar relationship? And so the ambient temperature throughout these three conditions was between 8 and 12 degrees Celsius. And so we tried to make the inference that dry heat exchange would be similar, and thus any proportional rise in heat production would be an equivocal increase in the evaporative requirements for heat balance. And albeit, despite the limitations, we can still see this linear trend where the more heat you're producing, and consequently, the more heat you need to lose through evaporation, you'll see a greater rise in sweating. So how does this conceptual determinant of sweating through the heat balance equations satisfy what we've seen with traditional thermoregulatory control? So let's take this back to the idea of a simple exercise bout where someone is producing heat for 60 minutes or exercising for 60 minutes. At the onset of exercise, as you see at the graph in the bottom left, the heat loss requirement shoots up immediately and then stays stable for the rest of exercise bout. And there's this delay in our actual heat loss, which is the blue line, to where we match the heat that we need to lose to maintain heat balance. And this net difference between the two is what causes our core temperature to rise, and consequently thermoeffective responses to occur, such as sweating, until we hit a nadir, where we hit this plateau where we've reached steady state. Now let's bring back our graph from before, where we had these different onsets and thermal sensitivities amongst individuals, A, B, and C, if you will. And let's say we need to attain this sweat rate to achieve heat balance. So amongst all these three individuals, if they had starting at different temperatures and then achieve this steady state sweat rate, we would expect something like this, where we see the sweat rate at steady state is similar between all three, but we actually see differences in the core temperature response during exercise, at least in an absolute term. But if we then go and superimpose them on each other, in fact, it's probably about the same change. And so this brings us to bringing both paradigms together, and perhaps one's complementary to the other. Now, what happens when we have a maximum sweat rate of an individual, but yet we exceed it with the sweat rate required for heat balance? And this is going to come into the next topic that I'm going to discuss as the last kind of background info before I start showing data for studies, is this concept of maximum skin wetness. And skin wetness was a topic that, or a key idea that was brought about by Gaggy in the 1930s. And it's this idea of how much skin surface we can saturate with sweat. Maximum skin wetness is the maximum portion of the skin surface that we can saturate at maximum sweat rate. And in works from the 80s by Victor Candace, we know that there's a range of maximum skin wetness that can be achieved. It was thought to be between 85% to 100%, where an unacclimated individual could achieve about 85% of maximum skin wetness at maximum sweating. So now if we take this individual and we put them in a condition where the required skin wetness to achieve heat balance is 93%, we would expect that their change in core temperature would go something like this. And we would denote this as an uncompensable heat stress condition. They're unable to achieve heat balance because they cannot maximally saturate their skin with sufficient sweat. Now, if we put this individual through something like a heat acclimation protocol, we know that we can actually almost achieve, if not achieve, maximum skin wetness, which is a theoretical limit of 1 on a nude person. And if we put the same individual under the similar heat load of 93, or similar maximum or required skin wetness for heat balance of 93%, we would expect a change in core temperature like this. They're compensable. And this idea of compensability is attainable because they physiologically are able to attain that skin wetness required. And this was actually an idea that a component that was often disregarded in a lot of the heat acclimation protocols, looking at thermoeffective responses in trained individuals with and without heat acclimation. And so we really didn't know where a person's maximum skin wetness would rely and how this would alter someone's responses in either a compensable or an uncompensable scenario. So one of the studies that we conducted to look at this and a couple other ideas was a training study during my PhD. And we had people come in for a battery of testing. So we did their VO2 max test, we did a maximum skin wetness assessment. They then undertook a compensable and an uncompensable heat stress trial. We trained them with supervised training for 4 weeks, 4 sessions a week. 3 sessions were steady state and 1 was HIT. The purpose of this was twofold. It was one, to increase their VO2 max by at least 10%. And it was also to induce something that's been coined as partial acclimation associated with training. We followed this up by repeating this gamut of testing. And then we put them through a 6-day heat acclimation protocol. This 6-day heat acclimation protocol consisted of 90 minutes a day of treadmill march in a hot and humid environment at a fixed percentage of their heart rate max. And we did this design specifically because we knew that heart rate is one of the most fastest responders to adaptations to heat acclimation. So if we fix the heart rate, progressively the intensity is going to increase throughout the the heat acclimation protocol, and therefore the heat load will be greater throughout the protocol. And then we had them come back. We didn't do the VO2 max test, but we did those 3 assessments again. So the first thing that we're going to talk about is the maximum skin wetness as it changed through a function of partial and complete heat acclimation. So traditionally, we had thought that the unacclimated individual has maximum skin wetness of about 85% or 0.85. And in fact, what we saw with the pre-training group, or sorry, the group prior to training, was their maximum skin wetness was even lower than that. It was about 0.72 or 72% that they were able to fully saturate in sweat. The numbers denoted in the circles is the VO2 max ranking at the start of the training protocol. So 1 being the person with the highest VO2 max, 8 being the person with the lowest VO2 max. Following training, when we reassessed, we saw that their maximum skin wetness had increased to about 0.84 or 84% of their skin surface. And then following heat acclimation, the average was 0.95. So we were observing that people were showing that physiological adaptation of being able to more saturate their skin in sweat. And this was confirmed with local sweat rate at the point of inflection. In our trials, we saw that when they'd reached maximum skin wetness, their local sweat rate was higher, both on the arm and on the back. We've seen that the activated sweat gland density at inflection had also increased both on the arm and the back. This was done using the starch iodine technique adjacent to the sweat capsule. Mathematically, however, when you relate both together, the sweat gland output was not changed between arm and back for pre-training, post-training, and post-heat acclimation. So we needed to do that first component of the study to be able to ensure that when we provided a compensable and uncompensable heat load in this group, they were both, the skin wetness required was both attainable or unobtainable. And so our compensable condition during the pre-training, post-training, post-heat acclimation was at a skin wetness required of 0.6. So regardless of their partial or complete heat acclimation status, they should be able to be compensable under that condition. And we also wanted to test them under a condition where it was always uncompensable, regardless of their acclimation status, to see how this might alter the thermoeffective responses, the sweating responses during these 2 different heat loads. So first thing I'm going to go through is the compensable condition. And what we saw was that classical description of with partial and complete heat acclimation, there's a reduction in core temperature for the same workload. So you see the baseline core temperature in the upper left graph. Pre-training blue, white is post-training, and gold is post-heat acclimation. There's a main effect of lowering the absolute core temperature during the exercise bout. But when you express it as a change, we saw no difference between all three conditions. Now, most shockingly to us was that the local sweat rate on the arm was marginally higher during progressive acclimation, whereas on the back, there was no difference. This translated to about 50 grams more whole body sweat loss over the 45 minutes in the post-heat acclimation versus the pre-training condition. So it wasn't a lot. However, when we went to the uncompensable scenario, and effectively all we did was we kept the same evaporative requirements for heat balance between the compensable and uncompensable. All we did was increase the humidity in the room. We saw again that similar trend of the reduction in absolute core temperature as you progress from pre-training to post-training to post-heat acclimation. And when you express it as a change, partial and complete heat acclimation showed a reduction in core temperature relative to pre-training after about 45 minutes of exercise. And this was corroborated with higher sweating on both the arm and back, suggesting that the partial and complete heat acclimation augments the upper limit for heat dissipation, so as denoted by the increases in maximum skin wettedness, whereas in a compensable condition, it may not play too much of an influence on the thermoeffective responses at steady state. Now, one of the questions we weren't able to answer with this one was the influence of fitness. Everyone was trained. So we had everyone going through a training program to increase their VO2 max, but we didn't have a subset of people who had not trained but had high VO2 max. But fortunately, we had data from prior studies that we were able to combine with this one to kind of give an illustration of what might have be the case and what's the actual determinant of these greater evaporative capacities. And so we had two groups. We had a fitness group and we had a training group. They were about 45 for the unfit and 55 for the fit for both the fitness and training components. And what we see is that the rectal temperature change over 60 minutes of an uncompensable heat stress, again, we see that main effect with unfit to fit, but the change was similar with similar local sweat rates. So, however, when we look at the training group, we see that the change in core temperature is reduced following training, and the local sweat rate was higher with training, suggesting that it's the physical act of training and that heat load that's occurring during the training that's inducing these thermoregulatory adaptations, and it's not the impact of solely having a higher VO2 max. So what we showed in these few studies now is that there's the higher, or the lower core temperature with training, at least during compensable heat stress, doesn't alter the thermoeffective responses, such as sweating at steady state. But we wanted to try and manipulate core temperature somehow. And we thought of one way through the use of the diurnal variation in core temperature. So thinking that if core temperature is higher in the afternoon versus the lower, we might expect to see differences in thermoeffective responses in relation to the traditional control theory when you conduct the exercise in the afternoon versus the morning. And so we developed this rather messy kind of schematic here at the bottom, but all the arrows reflect the comparisons that could be made within it. And so what we did is we compared AM versus PM at the same evaporative requirements for heat balance. And this would enable us to have a different core temperature at the start of exercise to see how this might affect later or downstream thermoeffective responses. We then compared between conditions with the same evaporative requirements, but a different absolute ambient core temperature, so 33 degrees Celsius and 23 degrees Celsius. We matched EREC by modifying the heat load in either condition. And then we took the other comparison, which was a matched heat production, but in two different environments, so we have differences in the evaporative requirements to truly see if there's an effect of core temperature and skin temperature because of the plays in ambient temperature on steady state sweating. So when we look at the one condition where we had the same heat production, but differences in EREC of 200 and 275 watts per meter squared, we had a higher esophageal temperature at the higher evaporative requirements for heat balance. And then same thing with skin. And as well, we saw higher sweating of the arm the back, and whole body sweat rate at steady state amongst all three conditions, or amongst all three, with the higher EREC. However, when we were matching for EREC between AM and PM, so remember that this would cause a shift with a higher baseline core temperature in the afternoon versus the morning, but it's effectively the same condition being replicated. We saw a higher core temperature, esophageal temperature in the afternoon, with similar skin temperatures between both. And we saw the same sweating both locally and whole body when fixed for EREC. Again, we did the same matched EREC, but in two different environmental conditions. So to match EREC between those, we had to alter heat load so that we'd have a higher heat load at 23 degrees Celsius versus a lower heat load at 33. And we saw a higher core temperature, again, in the cooler conditions versus the hotter. Conversely, we saw differences in skin temperature between the cool and the hot condition. However, again, we saw similar sweating locally on the arm and the back, and whole body sweat rate was similar as well during that steady state period from 45 to 60 minutes of exercise. So collectively right now, we have a bulk of evidence to show that EREC is the determinant of steady state sweating. However, one could say that we pre-planned this and we said, well, we might expect to see this because all we're doing is shifting with a diurnal variation, the baseline core temperature. So we came up with another study design while I was in Australia that was quite cumbersome to pilot, but demonstrated some pretty interesting results. So what we did, we took people and we heated them up with a water perfused suit initially by about a degree change in internal temperature. And then we made them exercise for 60 minutes afterwards at an evaporative requirements for heat balance of about 200 watts per meter squared. It took a lot of piloting to get this to work right, but the transition from heating to exercise was less than 3 minutes. And you'll see why in a sec. So we also had this exercise conducted in 38 degrees Celsius and 50% relative humidity. So I'll show you the core temperature responses during the exercise bout and the skin temperature responses. So on the upper left hand, we'll see the white dots as the whole body heating and the gray dots as the control. And what we were able to do successfully during the steady state period or during exercise was to maintain a higher absolute core temperature with the people with whole body heating relative to the control condition, so that during steady state, we had effectively a 0.5 degree difference between both states. However, skin temperature became similar between both. Now, surprisingly, this was a sweating response. We saw locally on the arm, because it was the most secure place that we could place a sweat capsule, that sweating progressed downwards after you got out of the suit. However, when you reach steady state sweating was similar between both whole body heating and control conditions from 45 minutes to 60. And again, whole body sweat losses here, so that disproportionate difference between that first non-steady state period was about 190 grams difference with whole body heating versus control. However, when you look at the steady state period, the difference is abolished, and the accuracy of our scale in Sydney was plus or minus 2 grams, and the net difference between these two bars is 5 grams. So we were able to almost successfully take apart the core temperature and skin temperature modulation in this design. So that kind of brings back this idea of what's controlling steady state sweating. And this is we're not the first people to suggest this or to put forth these tenets. It was actually done by Werner in 1980, where he's showing that perhaps it's the passive system and the flux around the passive system that's causing these thermoreceptors to integrate and then cause the actual control of onsets and thermal sensitivities to incorporate back to the sweat glands. And this is the feedback loop itself. So really, the passive system is just a consequence of our onset and thresholds for sweating itself. And once we get to steady state, these are just finely tuned. And I'm sure Zach and Davide are going to touch more on the behavioral aspect of this in their upcoming talks. So again, the key points, EREC determines steady state sweating during compensable conditions, independent of core temperature, skin temperature, circadian rhythm in a sense, and heat acclimation status. Partial and complete heat acclimation just expands the range of compensable conditions by increasing someone's maximum skin wetness potential. The sweating adaptations associated with heat acclimation are most evident during uncompensable heat stress. So if you want to see if someone has demonstrated improved evaporative capacity, it's best to test this under conditions you can confirm are going to be uncompensable. And lastly, it's not fitness per se, but probably more so the frequent physical training, which augments that upper limit for heat dissipation. So again, thank you guys for giving me the opportunity to talk. I'd like to just take a second to thank everyone that's had to listen to this talk before in the past and has provided me all the support, both past and present. Thank you.
Well, thank you very much, Nick, for this comprehensive and integrative presentation. I will allow myself the first question, if it's okay. It essentially pertains to the training effect or the fitness effect. Yeah. In terms of what I'm curious about is you nicely showed the effect of baseline testing or the training of these individuals on the subsequent thermoreg responses. But I'm curious to know your opinion on the fact that how much of the training effect per se during the for example, 10-day heat acclimation actually induces the thermoregulatory effect in the end, and how much of it is related to the actual effect of heat per se? Did I make it clear? Yeah,
that's a very good question. I think just breaking it down would be, you have to challenge something to get it to adapt. And so if you're challenging your sweat glands in this effect for thermoregulatory responses, because it's effectively what we're improving our heat dissipation, and the largest modifiable way is sweating. So during heat acclimation, you've got the combination of both. You've got the heat stress from the environment and you've got your heat production. So those 10 days, you'll progressively, hopefully, increase your sweat output or local sweating through some mechanism. With training alone, you might not have that heat component. So you can isolate a bit the effects of a heat load per se. So I think really the adaptation that's occurring is just a consequence of how much heat you need to dissipate. And if you're testing your sweat, if you're stressing your sweat glands to sweat, they're going to sweat. If you make them stress a bit more to sweat more, they're going to sweat more. And that's where your adaptation will occur. I don't know if it's a function exclusively of the training component. I think it's a consequence of the thermoregulatory requirement during those conditions. There's some great work by Heenan in the 60s who had swimmers versus runners, and they show that swimmers don't sweat as good as runners, but yet they have the same fitness or similar VO2 max. Yeah, I agree. Yeah, thank you very much. I think it's a tricky question and hard to discern the effects of both, but I agree that if we focus on the output, that's like a good strategy. And a colleague of mine, Alexandros Sotiridis from Greece, recently also tried to investigate in that regard, and it's definitely something to look into further in terms of thermal adaptation. Then I will allow another. Oh, so we have two more short questions. One is more applied on an applied area, and mostly related to uncompensable heat stress. In particular, how does heat balance work when there's limited evaporative cooling? For example, in the conditions of personal protective clothing, or firefighters or whatever like that, where evaporation is essentially so limited that it's uncompensable by default, let's say. Yeah, that's a great question. So you're effectively changing the evaporative maximum capacity of that individual by having garments or whatever on them. So you're starting to get in the nuance between tolerance and thermoregulatory drive. And I know Stephen's done some work on the tolerance aspect with having people heat acclimated or trained and then being sequestered to a uncompensable heat stress till exhaustion. And you see that people tolerate it more. But within a thermoregulatory standing, your sweat, you might be able to saturate more of your sweat or skin with sweat, which may facilitate a little bit more evaporative heat loss, but the difference as you reduce your Emax to your potential sweating, or the amount that you can actually lose, becomes smaller and smaller. So it's almost negligible under these conditions. So you'd be probably most looking at the tolerance component of it than the actual thermoregulatory component. Okay. Thank you very much, Nicholas. I will leave you to answer to Andrew's questions
then subsequently in Q&A forum, and would like to thank you again for your great contribution. And now we'll hand it over to Zach. The floor is yours, Zach.
Okay. Can everyone see that? Awesome. Okay. First, I'd like to say thank you for the opportunity to share some of our work, and I think the virtual sessions that that are out there have been really good for both myself and some of our trainees. So today we're going to talk a little bit about some of our recent work looking at autonomic and behavioral interactions in thermoregulation, particularly during exercise or heat stress. I would also like to note at the outset, or acknowledge at the outset, that most of this work was led by Nicole Vargas when she was a postdoc in our lab at the University at Buffalo. So just as an outline for what we're going to be talking about, we'll briefly introduce why we're interested in behavioral thermoregulation, essentially when body temperatures are elevated, and then we're going to transition to some of our work looking at signals contributing to the voluntary decisions to seek cooling, introduce the potential role of skin wettedness from a little bit different perspective than what Nick mentioned, addressing some of the methodological hurdles and some of the experimental evidence, and then we'll bring it home with some working talking points and a working model. So why study behavioral thermoregulation, particularly during heat stress? I believe virtually everyone on this call is familiar with graphs that look something like this, whereby we know the Earth is getting hotter, and 2019 was the second hottest year on record. And we've also probably very familiar with these type of figures where we can clearly show that with increases in ambient temperature, we get increases in daily mortality or morbidity or pretty much whatever metric you want to look at. So this kind of highlights the potential importance of understanding how the body regulates temperature, and this is where a lot of our work has come in. So we can quite in a very simple manner look at human temperature regulation from two perspectives. The first, which was nicely summarized by Nick, involves the autonomic responses, particularly during heat stress. We're talking about cutaneous vasodilation or increases in skin blood flow, as well as sweating. But another aspect of temperature regulation involves our behavioral responses. And by this, we mean the voluntary modification of that thermal stress. And that includes aspects of physiology, such as body temperature, and as we'll discuss today, skin wettedness, as well as aspects of psychology. Examples are varied. There are tons of examples. Simple ones are changing the thermostat in a room, turning on or off a fan, taking off a coat, putting on that coat, etc. And I think most textbook kind of definitions of human temperature regulation will acknowledge that that the behavioral responses are often considered to be kind of the more preferred and powerful response. Best example I can think of is if you're sitting in a warm room and you have a coat on, you don't just sit there and sweat. You take that coat off first. But it turns out there's not too much empirical data to kind of compare the importance or the relative importance of autonomic compared to the behavioral responses. So for this, I think it's worthwhile looking at some work in ectotherms, who ectotherms have very little capacity for autonomic thermoregulation, but they still are able to regulate their body temperatures very well. And that's nicely shown here. These are data in lizards from way back in 1948, where you can see air temperature, is moderately warm, but due to almost solely behavioral responses, these lizards are able to regulate their body temperatures much hotter than the ambient air. And the only way they could do that is via behavioral mechanisms. So to kind of better emphasize this point, here we have data from a synopsis published in the 80s. We could see they looked at the relative importance of behavioral versus autonomic responses, again, staying in ectotherms. So this is for the maximum change in body temperature for a 1 kilo animal, so quite a small animal. And you can see the behavioral responses are much more powerful than the autonomic responses in ectotherms. And there's reason to believe that this might also be the case in homeotherms. So for the most part, it's pretty well accepted that the behavioral responses are much more effective at controlling body temperature compared to the autonomic responses. So why are we particularly focused in the behavioral side? But bring it all back to the warming temperatures. A paper published in 2010 concluded that kind of mapped out how hot things were going to get in certain areas with given levels of global warming. And these authors found that a global mean warming of approximately 7 degrees C would create small zones where essentially we will not be able to thermoregulate via autonomic mechanisms. And so for us to habitate those areas, the only way we can regulate body temperature is via the behavioral responses. So it's important to understand what's going on. So now we'll transition to what are some of the signals contributing to decisions to seek cooling. So we're going to focus in on the hot side here. So Nicole and I published last year a paper where we kind of outlined the knowledge regarding what signals are contributing to this. And this is one of the figures from this, where we have an increase in core body temperature. That increase in core body temperature ultimately stimulates an increase in thermal discomfort. And it's that thermal discomfort that is the primary perceptual driver for seeking out behavior. And these behavioral responses can either directly impact core temperatures. So in the instance of elevations in metabolic heat production, say during exercise, we can slow down that exercise, and that can directly modify core body temperature. Or we can seek cooling by cooling the skin, which ultimately acts to reduce core body temperature. It turns out that this was a relatively simplistic view, and part of the reason we have this view is because it's relatively easy to measure core and skin temperature. But if we go all the way back to the 1930s, we can see that that core temperature and/or skin temperature are not the sole drivers of this paradigm. So this is some work from Winslow et al., published in 1937, and where we adapted and we showed is if you have people sit in a hot room for a long period of time, you see skin temperature is relatively high. For an example, core temperature rises and ultimately plateaus, but thermal discomfort continues to go up over time. So if we were going to model thermal discomfort based on everything that's happening on the left side, we would expect thermal discomfort to also plateau, since core body temperature is no longer going up and skin temperature is no longer going up. But what happens here is that we have a continued development of skin wettedness. And so Nick nicely defined skin wettedness, but in this case, it's in the same definition here. It's a proportion of skin that's wet at any given time. And we think of this as essentially the sweat buildup on the skin. And so because of this kind of relationship between thermal discomfort and skin wettedness, amongst some other analyses, they were able to conclude, and I think rightfully so, that the wetted area of the skin is the major determining factor in comfort on the hot side. And this was further supported more recently by data from George Havenith's lab, where they show a nice linear relationship between thermal discomfort or thermal comfort, which is on the y-axis, and on the x-axis, the skin wettedness. So you can see a linear relationship whereby elevations in thermal discomfort elevations in skin wettedness bring about increases in thermal discomfort. So this led us to the question, does skin wettedness contribute to decisions to engage in cool-seeking behavior? And as we tried to approach this question, we had a couple of methodological hurdles that I wanted to point out. The first was, how do we measure whole body skin wettedness, particularly when we're looking at dynamic changes in skin wettedness, as opposed to the more conceptualized approach that Nick described earlier. And then the second thing is, how can we measure cool-seeking behavior without influencing skin wettedness? So for instance, if you actively cool the skin, that will directly alter skin wetness by potentially manipulating sweat rate, as well as manipulating the partial pressure gradient between the skin and the air. So we're just to briefly address some of these methodological hurdles. The first one is a little bit more straightforward. So to understand how we can measure whole body skin wetness, think of local skin wetness essentially as the partial pressure of water on the skin. And so really it comes down to how can we accurately measure the partial pressure of water on the skin. And because we're going to measure it locally, we want to measure it at multiple locations over the body to get a better idea of whole body skin wetness. So think of this as analogous to how we measure mean skin temperature. So what we did is we used hydrochron eye buttons. These are sensors that measure temperature and relative humidity, and we can back calculate into the partial pressure of water. So this is an example of what it looks like. There's the humidity sensor here. The question was, how far off the skin should we put these sensors? The standard way to do this is about 2 millimeters off the skin. The problem with that is, or the challenge is that as sweat gets put up onto the skin, if you get a drop of fluid inside that sensor, it's super saturated. So we'll always read a reading of 100% relative humidity. And we couldn't essentially run that risk. So we did a series of essentially physics experiments to try to figure out how far off the skin we can measure humidity without achieving supersaturation. So we had a student in the lab who did some work where we had different heights of the sensors off of a saturated paper towel. So think of this as completely wet skin. And we had this mat that we controlled at various levels of skin temperature. And what we ultimately found was that if we raise the humidity sensor off the skin 6 millimeters, that results in a partial pressure of water on the surface of virtually equivalent to what happens when you raise it off 2 millimeters. So from this perspective, we now had a way to measure skin wetness, particularly if we take these little sensors and we put them over a large portion of the body. So all of the data that you'll see later is somewhere between 8 and 10 sites. So now let's transition to how we measure cool-seeking behavior, again, without influencing skin wetness. To do this, we had to go back to some of the classic work from the early 70s by Michel Cabanach, who really did, again, a lot of the seminal work in this area of thermal behavior. And what they did was they allowed people to control the temperature of their hand at thermally comfortable, and then they modified the ambient conditions to get an idea of the desire to behaviorally thermoregulate. So here we have an example where they expose people to drops or progressive decreases in ambient temperature. You can see, again, these are data that are redrawn, but you can see you get slight progressive reductions in skin temperature over time, and ultimately slight reductions in index of core body temperature. But when the participants regulate the temperature of the glove, so their hand is inside of a glove and they can regulate the temperature of that glove so that it's always thermally pleasant or thermally comfortable, you can see that glove temperature rises over time. So what we did is we wanted to modify this approach from the glove and use an area of skin that we know is very, very sensitive to heating and cooling, and that's the neck. The neck turns out is the most perceptually sensitive area to both heating and cooling. And so it took us some time to figure out exactly how to do this, essentially without especially choking our participants. But here we have an example of someone wearing what we call the neck device while cycling. And what this neck device is a series of tubes. The green tubes are filled with antifreeze that can be, the maximum cooling capacity of it is a -20 degrees. So it's very, very cold. And this is under behavioral control. So the participants have their hands on either a button or a valve, and then control the flow rate of the fluid through these tubes. And then The white, or the clear tubes, are constantly perfused with 34 degrees C water. So when you have the valve open, neck temperature will fall. But when you close that valve, you start to get increases in neck temperature. So neck temperature does not just stay constant the whole time. And what this really allows for is an indication of thermal behavior. We fully admit that this is not truly thermal behavior, as in it does not, it will not impact the thermal status of the body, but it provides insights into both the desire to initiate that behavior, as well as the magnitude of that desire. So there we have our models. And then now what we want to do is see how these models contribute, or if we use this model, we can see how skin wetness contributes to the decisions to seek cooling. So the first study I want to highlight here, we tested the hypothesis that skin wetness contributes to cool seeking behavior to a greater extent than skin or core temperatures. And this is really rooted in some of the foundational data that was published by Winslow in the 30s. To do this, we elevated body temperature by having people conduct 30 minutes of moderate intensity exercise, and then we had them recover for 120 minutes. We had them exercise in a moderate environment, and in this case, participants essentially had control of a valve, so they voluntarily adjusted the neck device temperature. So here are core body temperature and mean skin temperature data. So on the x-axis is time, so exercise was 30 minutes and 120 minutes of recovery. And you can see we get, as you would expect, increases in core body temperature, very little change in mean skin temperature. And perhaps most importantly, you get a nice rise in skin wetness that is sustained throughout a lot of recovery, but ultimately abates by about 90 minutes into recovery. So perhaps not surprisingly again, we see that when we exercise, ultimately people decided to behaviorally thermoregulate. So they decreased the temperature of their neck by reducing the temperature of the fluid running through that neck device. And so here we have, during exercise, people are seeking cooling, and then during recovery, it gradually restores up to what it was before exercise. So we have a nice kind of on-off response here. And this allowed us to go back and what we did to try to understand how important wetness was relative to core and skin temperature was we used essentially linear regression. And using those beta coefficients, you can get an idea of the relative importance of core, skin, and skin wetness to the observed behavioral response. And here is essentially a synopsis of this. And what you can see is that skin wetness contributed about 50% of the signal to neck device temperature, compared to both core and skin temperature, which really comprised about 25% of that signal. So from this, we showed that skin wetness is a greater contributor to cool seeking behavior compared to both skin or core body temperatures. But we can't really make this statement with any causality. We really showed a association, and so hence the likely in this header. So what we wanted to do is follow this up and try to show causation, that really skin wetness does contribute to a greater extent. So we designed a study to test the hypothesis that increased skin wetness stimulates a greater or larger cool-seeking response during heat stress, and that this happens independent of differential increases in skin or core temperature. And this became methodologically challenging. The reason is because if you manipulate skin wetness, oftentimes that results in changes in skin temperature by manipulating the rate of evaporation. So for instance, skin wetness can be higher in a highly humid environment in order to kind of help facilitate evaporative heat loss. But it turns out that in that case, you also have elevations in skin temperature. So to do this, we had to take a little bit different approach. We used a passive heating model where we had people dressed in a tube-lined suit, and we perfused water, warm water throughout that suit, and that helped us to clamp skin temperature. And we piloted this extensively. I give Nicole a lot of credit for this, and to make sure essentially that by clamping skin temperature, we could ultimately result in core temperatures that were not different in these cases. And then what we did is we manipulated skin wettedness by modifying the ambient humidity. So what we had was a baseline period where we had low ambient humidity. In one trial, which turns out to be 30% relative humidity, these are the absolute humidity data, we kept the relative humidity in the room the same. It was 27 degrees C in the room at this time. And then in one trial, we raised the humidity in the room. So it took about an hour to increase the humidity in the room so that it was stable. So we increased it to 70. And then we began passive heat stress for the remaining hour. And this allowed us to independently manipulate skin wettedness while hopefully keeping core and skin temperatures the same. In this case, we used the same neck device temperature here. You can see it in the supine position where we can keep really good contact with the skin. But in this case, the participants pressed a button, and every time they pressed that button, they got 30 seconds of cooling through the tubes or through the neck device, which, as you'll see, allowed us to give a little bit different insights. Okay, so what did we do? Well, again, due to the extensive piloting that Nicole did, we were very confident that we're going to be able to manipulate skin wettedness. And as you can see here, particularly focusing in the passive heat stress section, we get greater skin wettedness in the 70% relative humidity trial versus the 30%. So we were able to manipulate and create a low versus high skin wettedness condition. And also, if we look at the body temperature responses, core body temperature did not change, was not different between the trials throughout, and mean skin temperature was effectively clamped. So again, the passive heating and the model looked like it worked. So how did this translate to decisions to seek cooling? So the first thing, because we used the button clicking model, this allowed us to get an idea of the total time spent in cooling. So, and as we can see, whenever you have high skin wettedness, you spend more time in cooling. There's a greater drive to seek cooling. And this was translated to lower neck device temperatures during the passive heating, particularly at the end stages of passive heating. So when core body temperature is elevated, skin temperatures are elevated, but you have more skin wettedness, that results in a greater drive to seek cooling. And we wanted to further this up to try to get an idea of what signals people are listening to. And so to do this, we turned to segmental regression, which most people in this audience, I'm sure, are very familiar, as it's a common approach in thermal physiology. But here, what we did is we plotted neck device temperature over mean skin temperature for every participant. And we draw two lines, essentially. And then the threshold or the breakpoint of this line gives us an idea of the mean skin temperature at which people decided to begin to behaviorally thermoregulate or seek that cooling. And then the slope of that line thereafter is termed the sensitivity of that. And so using this, what we could see is that the mean skin temperature threshold upon which behavior was initiated, upon which people decided to start cooling, was lower. So we've increased essentially our sensitivity to a given increase in mean skin temperature. But after that threshold is met, you can see there are no differences in the sensitivity. So after we've achieved that, the response rate is essentially the same. So from this, I think we can conclude with more confidence than our more associative data that skin wettedness augments cool-seeking behavior during heat stress. So I want to wrap up with a few take-home points, and then we'll introduce a model that I think ultimately will segue very nicely into Davide's talk. So hopefully you can take away that behavior is our most preferred and powerful thermoregulatory modality, and that there's a need to understand the mechanisms and modulators of thermal behavior, particularly during heat stress. Also, I think there's relatively convincing evidence that increased skin wetness augments cool-seeking behavior when body temperatures are elevated. And I'm going to leave with this, that the mechanisms to date remain largely unexplored. So we really don't know much about how the skin wetness contributes to cool-seeking behavior. And so this has led us to kind of a working model that we're going off of to try to understand what's happening. So during heat stress, we have increases in core and or skin temperature. We know that this is ultimately conveyed via the insular cortex to a change in thermal comfort or thermal discomfort. And this brings about a behavioral response that ultimately will help restore core temperature or skin temperature back down to normal temperatures. But we also know at the same time there are signals there to the preoptic anterior area of the hypothalamus. And we know that this is kind of a thermoregulatory control center that's going to ultimately bring about sweating. And with this sweating, we know we're going to generate skin wetness, again, as highlighted by Nick's talk. And then this ultimately can result in an increased perception of skin wetness. And Davide will talk about some of his really elegant work looking at how skin temperatures and mechanoreceptor activation contribute to this. And that we believe, although there's no empirical evidence yet to date, we believe that this also can result in an increase in thermal discomfort. And perhaps most importantly, kind of our hypothesis is that this wettedness, when in the presence of elevations in core and skin temperature and already kind of elevated thermal discomfort, this wettedness magnifies the signal. And that ultimately elevates thermal discomfort to such a point that this further drives up the desire to seek cooling. And so this is kind of our working model to date, but we haven't really been able to dive into the mechanisms quite yet. So with that, I'd like to say thank you, particularly to, again, Nicole Vargas. She really led a lot of this work, all of our collaborators at the University at Buffalo, and also I'd like to give a special shout out to Rob Gathercole at Lululemon. Lulu supported all of this work, and they've been an excellent partner throughout all of this. And I'm happy to answer any questions. Thank you.
Yeah, thanks a lot, Zach, for this really great insight into the complexities of the discerning of the effects of skin wetness and controlling other factors to assess the behavioral responses. We see that this is a complex area and requires really much planning and much smooth methodological approaches. I will just give you two short questions from the public, just briefly. And the first is regarding the effects of different body regions or different regions of skin wetness, and if they contribute to the same magnitude in terms of the cool-seeking behavior.
Yeah, it's a really good question. And I think we don't know. I think if we go look at some of Davide's work, we know there are regional differences in the perception of skin wetness. And so from that perspective, I think that it's likely that regional factors contribute, but how that exactly translates to cool-seeking behavior, we don't know yet. But I would hypothesize that would be the case.
It would be the case, yeah. And then there's a nice question from Geoff Combs. In particular, he's curious about if you have any specific considerations in terms of participant selection for this type of studies, because you're measuring behavior essentially, and if you include people who have previously done this type of heat adaptations or heating studies, or they're trained, or how do you perceive, or maybe just what are the inclusion or exclusion criteria generally for this?
Yeah, it's a really good point. We do our best to make our group as homogeneous as possible. We make sure, at least for these studies, they're not acclimated. They're all physically active, but not necessarily athletes. we test them for, basic kind of cognitive ability using very kind of clinical scales to show that they're at least in normal ranges. So they're all really, really good points. I think the probably the most important thing though is we do a lot of work familiarizing people with the approaches. So they've all gone through essentially a light version of the study by manipulating that neck device. So they know exactly what it feels like. They're very well familiarized with the scales that we're using and things of that nature. So that's a very good point. And I think it comes down to some of these studies, it just takes a lot of familiarization, a lot of kind of attention to detail when it comes down to collecting the data.
Okay, great. Well, thanks again for your contribution and presentation. I would like to just ask you to unshare your screen now, and then I will pass it on to Davide. As I mentioned before, last but not least, Davide, go ahead.
Thank you. Thank you very much for the introduction and for the opportunity to talk to you today. This is a great initiative, particularly at this difficult time. So without any delay, I'm going to dive straight into the outline of the talk for today. It was primarily is going to focus on providing a fundamental and applied overview of how we sense wetness on the skin. And I'll start off with a little bit of background, most of which has been already covered by Zach and Nick. Move into some of the psychophysical mechanisms related to wetness sensing, primarily looking at cold and touch inputs on the skin. And then I'll try to share a little bit of knowledge on the likely peripheral and central neurophysiological mechanisms that allow us to integrate wetness perceptions. And I'll then finish off with a little bit of work that we've done recently, looking at some independent modulators of skin wetness, namely sex, exercise, and aging. So as Nick and Zach very nicely put earlier on, from the thermoregulatory standpoint, humans are relatively fragile in the sense that we really strive for thermal homeostasis. And if on one side we are relatively limited in terms of, the upper limits of our autonomic thermoregulatory system, as Nick nicely put in terms of the amount of sweat that an environment can take by evaporation or the amount of sweat that an individual can actually produce. On the other side, behavioral thermoregulation is a very powerful mean to help us adjusting to thermal stresses, to the extent that I'd say against the odds, as a species, we've been very successful in exploring and inhabiting very extreme environments across the globe. And if you think of space travel, even beyond there, and that's very much due to our ability to sense the properties of the surrounding thermal environment and respond to it in an adaptive fashion. And of course, as Doug nicely showed us, we know the only species out there that does so. And so really the idea is that we use our thermoregulatory behavior to adjust our thermal states and maintain thermal homeostasis. And that's very much driven by thermal comfort and any displacement from that thermal comfort range that we tend to relate to. And so when we talk about thermal comfort, we consider this as a conscious indicator of thermal balance. And whenever there is a displacement outside of that range of body temperatures that we feel we're comfortable within, then we will experience discomfort, whether it's heat-related or cold-related. Now, the interesting thing is that whenever you apply a stimulus on the body that helps reestablishing that thermal comfort, let's say cooling as you get hot, then that stimulus will be perceived as pleasant. And as Kabanak nicely showed in the 70s, pleasure is really the physiological currency of reestablishing those thermal homeostatic states, to the extent that the stimulus in itself can vary its hedonic value. And if you think, for example, of applying the same cold stimulus on somebody who's already cold, that stimulus will drift them away from the thermal balance, and hence why it feels unpleasant as compared to when you have cooling when you're hot. And so thermal comfort is really at the root of some of those behaviors, as Zach showed us. And I quite like Ken Parsons' model, which I've modified for the purpose of this presentation with regards to what's behind the concept of thermal comfort. And that really has to do with our ability to experience temperature and wetness sensation on the skin as a result of being exposed to either hot, cold, or humid stimuli. And most of the times what we will tend to do is we would compare those ongoing light sensations on the skin with the range of skin temperature and skin wetness that we have for comfort. And this is really feedback mechanisms by which any mismatch between the ongoing sensations and the ranges for comfort will trigger some specific behaviors, such as a behavioral adaptation in the cold. If we experience a thermal sensation that is below what the skin temperature for comfort is, we're likely to either increase metabolic heat production or increase clothing insulation if we're in the cold. And likewise, and Zach's model of cold-seeking behavior is a very nice example of that. If we experience an increase in skin wetness beyond the range of comfort, we're likely to trigger behaviors in the heat, such as either reducing metabolic heat production or reducing clothing insulation, or like in Zach's case, cold-seeking behaviors. And so from my standpoint, in terms of my research interest, I believe that there is a case for considering the way we experience temperature and wetness sensation as a key element of this chain of events that lead ultimately to those behavioral adaptation. And that's what I've been interested in the past few years in terms of understanding the physiology of temperature and wetness sensing. A little bit of a digress that is relevant in the context of the applications of this research, I believe. Obviously, increasing the understanding on thermosensory function is relevant to better understand thermoregulatory behaviors, but also, generally speaking, is relevant to understand somatosensation as a sensory function. And there is also clinical relevance, such that there is plenty of neurological conditions that are accompanied by sensory loss, temperature and wetness sensory loss. And in my lab, we are, for example, interested in multiple sclerosis as a model of thermosensory loss. And in the context of the practical applications of the research, obviously, sports clothing design often comes to mind as a way to apply the knowledge on how we sense temperature, wetness on the skin. But there is much more than that, particularly if we think of how to implement sensory feedback through neuroprosthetics in amputees, as well as integrating this knowledge into the design of virtual reality or optic devices. And so, if on one side, we, over the past 100 years, probably learned quite a great deal on the molecular, physiological, and perceptual mechanisms behind how a change in local skin temperature translates and is transduced into a neural inputs that is then coded by subcortical and cortical region to give us a sense of temperature, there's been comparatively little work done on understanding the perceptual mechanisms behind how we sense wetness and moisture on the skin. Despite, as Zach nicely reviewed, the role of skin wetness in driving thermal discomfort in the heat has been known for quite some time. Gagi did some seminal work showing the relationship between evaporative heat loss as an index of the buildup of sweat on the skin and thermal discomfort. And so what do we know about the way we sense wetness? Well, we know that we can sense it. We can sense moisture building up on the skin as well as contact with fluids or ambient humidity. Yes, today we believe we're not provided as a species with specific hygroreceptors in the skin that code for the sensation of wetness, despite there are examples in nature, particularly in the world of insects, where hygroreceptors and moisture sensitive receptors are indeed present. And so in a way, I like to think of this perception as an illusion to an extent. And I guess everyone who's ever experienced struggling to figure out whether the washing on the line is still wet or just cold might relate to this idea of the fact that we need to make sense of a perception for which we're not provided with a specific receptor on the skin. And so when I was doing my PhD in George Havenit's lab a couple of years ago, we started looking into building up a little model, trying to look at what biophysical and sensory cues might underpin this perception. And so when we have moisture on the skin, what would usually happen is that you have either evaporation of that moisture and therefore skin cooling and activation of thermoreceptors that are likely to give you a sensation of coldness, as well as movement of moisture across the skin that is likely to generate mechanosensory afferents that we tend to relate to the idea of stickiness. And so it's really the integration between cold and tactile inputs that give us that sense of wetness alongside some learning components. And so we started looking into the psychophysics of how cold and touch inputs might actually relate to wetness sensing. We started off with a little study where we looked at stimulating the skin of blindfolded individuals with a cold dry stimulus, generating different degrees of skin cooling. And interestingly, we found that for some specific skin cooling rates, individuals clearly experienced a perception of wetness, despite the fact that there was no contact with moisture. And then when we looked at the actual biophysical effects of droplets of water evaporating from the skin, we found that there was some resemblance of the amount of cooling that an actual droplet evaporating from the skin will give you as compared to the cooling stimuli that we provided during our experiments. And so in a way that led us to believe that, the brain doesn't really distinguish whether that cooling is driven by physical moisture or not, but it tends to associate that degree of cooling to the experience of wetness. Now, this also applies to condition of actual contact with moisture, and my PhD student, Kali Merrick, has done a study recently looking at the effect of moisture temperature on wetness thresholds of the finger pad. And when I talk about wetness thresholds, I refer to the minimum amount of moisture that somebody can sense, and therefore the lower the threshold, the more sensitive somebody is, in the sense that less moisture is needed for them to detect it. And what Kali found was that when we compared moisture temperatures to a temperature of 33 degrees Celsius, which resembles temperature, as the moisture got colder, there was a reduction in wetness threshold, just that people became more there was an increase in wetness threshold. So this gave a sense of this shift in sensitivity to wetness as a result of temperature. And just to give you an idea of the sort of sensitivity that we're talking about, when normalized over the surface area in contact with the thing and the substrate, the relative wetness threshold that Kali calculated at 25 degrees C corresponded to 0.002 milliliters per square millimeters. So we're very, very sensitive to tiny amounts of moisture on the skin. And beside the role of cold inputs, of course, we were aware of the importance of tactile stimulation of the skin, and anyone who has experienced touching warm water or sweating in a hot environment knows that you can sense wetness in the absence of cooling. And so we wanted to investigate a little bit more about the mechanical interaction of the skin under sweating conditions. And we designed a study where we had individuals performing exercise, wearing an impermeable coverall that would allow an increase and build up of moisture on the skin and sweat by trying to cut off as much evaporative cooling of the skin as possible. And then they underwent two conditions whereby in one they wore a first layer of clothing that was loose fit, and in other they wore a tight fitting clothing ensembles. The hypothesis being that given the same buildup of sweat on the skin across the body, the tight fitting condition, by reducing the amount of tactile interaction at the skin and movements of sweat across the skin, would have reduced individuals' wetness perception. And so we were successful with the study in making sure that the two conditions were equivalent in terms of increases in rectal temperature, mean skin temperature, buildup of skin wetness, as well as changes in galvanic skin conductance as an index of buildup of sweat within the sweat gland. Interestingly, we found that the individuals during the tight fitting trials, they experience lower wetness perceptions, both on the chest, the back, the arm, and the thigh, as compared to the loose fitting conditions, despite the fact that the two conditions were equivalent in the amount of moisture that was on these people's skin. And so in a way, this provided some evidence for the fact that in the absence of skin cooling, wetness is indeed modulated by mechanical and tactile inputs at the skin. And so at that point, we started to look into what potential central integration mechanisms could be behind the role of cold and touch inputs. And we developed a little model of what those pathways involved in wetness sensing could be. And we know the fibers and sensory neurons that innervate the skin and that responds to tactile stimulation and cold stimulation out of the A-type nerve fiber family. particularly we talk about A beta fibers and A delta fibers as coding both light touch and cold. And so we hypothesized that as compared to the role, for example, of C fibers that code for warm stimuli, it really is the central integration of afferents from A beta and A delta fibers that underpin the central mechanisms for wetness. And so we put this idea to test by having individuals psychophysically interact with warm wet, neutral wet, and cold wet stimuli with the same moisture content under static and dynamic conditions. And what we found, perhaps not surprisingly, was the fact that when the stimulus was cold, it was perceived as wetter than the neutral and the warm wet ones, despite the same level of moisture. And when they interacted with the stimulus dynamically and increasing the tactile stimulation, there was an increase in wetness, thereby providing evidence for the cold and touch input hypothesis. And so we decided to went a step further, and we wondered, okay, if this is an important pathway, what about if we knock it out by a selective neural block of A fibers and we repeat the same test? We would expect that those individuals would have a reduced wetness sensitivity. And so we use a compression ischemia block model, whereby we can progressively reduce activity in A fibers without impact on C fibers. And the individuals went and did the same experiments again. And overall, we found that as compared to when there was no block applied on these participants' forearms, there was a significant reduction in wetness sensitivity during the interaction with the same wet stimuli. And so this provided some evidence for the fact that, you know, we believe we don't have a wetness receptors, but it seems we've been good at developing a wetness sensation strategy, if you like, that leverages the central integration of these peripheral mechanisms. And so we tried to develop a little model explaining, you know, the variety of wetness sensation that you might experience in real life, such that if you have warm moisture on the skin, it is unlikely that you might experience that wetness sensation unless that moisture is moving across the skin and providing that tactile interaction. And a simple real life example is, I guess, a number of people might have experienced having a nosebleed, and often you don't realize it until somebody points it at you and say like, hey, you're bleeding, and you touch it with your fingers. And so that dynamic interaction provides that sense of wetness, given that the blood temperature is likely to be above skin temperature, not triggering any cooling sensation. Whereas on the cold side, even under static contact with cold dry stimuli, you can trigger that wetness sensation, which underscore this idea of illusions of wetness when you touch something that is cold and dry. And so this these findings about central mechanisms led us to go back and question this idea of humans as a hygroreceptor lacking species, because there is plenty of evidence from comparative physiology that both hygroreceptor provided species such as fruit flies and hygroreceptor lacking species such as nematodes, so the common roundworm, they sense wetness and humidity via mechanisms that leverage molecular channels expressed on primary sensory neurons that we humans have homologous on our cold and tactile receptors. And one of them is the transient receptor potential tryptamate, which is the one that has been discovered to code and transduce cooling into cold sensations. And is also the one behind the common experience of coolness and freshness when we apply menthol as a chemical agonist of this channel. And so an MSc student, Oliver Teipold, in my lab a couple of years ago, went to explore this idea of tryptamate as a potential peripheral mediator of wetness sensing in humans. And he came up with a nice model where he had individuals being exposed to a cold dry stimulus via thermal probe. And he also had a tryptamate agonist, a aqueous cream with a 5% menthol, and a vehicle that was a cream with the same chemical composition as the menthol, but without the active component. And it was measuring local skin temperature and skin blood flow at the contact site on the forehead. And what it was able to achieve over a 15-minute stimulation was a scenario where we had the cold dry stimulus inducing physical skin cooling and perceptual cooling, whereas the menthol induced no physical skin cooling but perceptual cooling, and then the vehicle cream induced no physical cooling, no perceptual cooling. And so it was able to then tease out the perceptual from the biophysical mechanisms related to wetness sensing. And it turned out when we looked at thermal sensation, wetness perceptions over the 15 minutes in these individuals, the mental conditions of the tryptophan agonist induced the coldest and the wetness perception despite limited physical cooling, below what was induced by the cold dry stimulus, and very different from what the vehicle cream actually induced in these individuals. And so this provided some initial evidence for the fact that tryptophan could be a peripheral candidate for a cold and wet sensing receptor in the skin. So with this, hopefully I've provided a little bit of overview on the psychophysical as well as some of the peripheral and central mechanisms involved in wetness. And now I'll finish off with some of the work that we've done on independent factors, modulators of wetness. So Alessandro Valenza, visiting MSc student from the University of Palermo, did a nice study in my lab where he looked at mapping wetness sensitivity to cold wet, neutral wet, and warm wet stimuli in both healthy young males and females. And beside the regional differences, what he found was that the two groups experienced the cold wet, neutral, and warm wet stimuli in a way similar to what we'd previously seen, such that given the same moisture level, the cold wet stimuli were perceived as wetter than the neutral and the wet and the warm one. And this suggested that both male and females might use similar integration mechanisms for that. However, he then found that the females were more sensitive to wetness than the males, particularly when it came to the cold wet stimuli. And it turns out that that's because those individuals reported a greater sensitivity to coldness than the males. And so it seems that sex modulates wetness perception by a temperature sensation dependent mechanism. Alessandro also looked at the effect of maximal exercise and whether this has some sort of analgesic effect on wetness sensing, as much as we know for temperature and pain sensations. And so he first established the relationship between thermal and wetness sensation such that he could find in the resting condition a typical U-shaped type of relationship, whereby the more intense the thermal sensation that one experiences, so either colder or warmer, the wetter the stimulus applied on the skin will feel. With the difference being that if the stimulus is cold, it feels wetter. And then it was able to show that following maximal running exercise, this relationship changed such that there was a shift down. So there was a reduction in wetness sensitivity and also a shrinkage of the relationship such that that is primarily driven by an exercise-induced reduction in temperature sensitivity. So again, exercise modulates wetness sensing by a temperature sensation mediated mechanism. And then finally, we went on assessing the independent effect of aging on wetness sensing. The hypothesis being that we know that sensory systems and the somatosensory system ages in humans. And so we wanted to assess whether that applies to skin wetness sensing. And Charlie Walgers did a nice study as an undergraduate student in my lab, where she looked at the effect of age. Unfortunately, the study was cut short because of the COVID pandemic. So I'm only presenting data for the 10 young and 6 old that she presented. But interestingly, even when we look at this preliminary data, what we find is that when Charlie assessed wetness sensitivity to a cold and a neutral stimulus on the skin across 6 different regions between old and young, there was an overall already statistically significant effect of age, such that the older group, the red bars here, were less sensitive than the younger group. And what I'd like to point your attention towards is that this difference seemed to be particularly pronounced on regions such as the forehead, the lower back, and the dorsal foot. Now, this is interesting because we know that these regions are particularly important in driving thermal discomfort. And so one could argue that if these older individuals are less sensitive over those regions that we know are important for discomfort, and skin wetness is important for driving discomfort, then those individuals might experience delays in engaging their thermal behavior, particularly in the heat. However, of course, this is speculative, and it might actually form the basis of a nice collaborative study with Zach's group, if he's interested. And so I'll finish off with a little bit of a wrap here. So in terms of the way we sense wetness, as far as we know, we don't have a receptor, yet I'd like to point out that the actual search for one has never been formally undertaken in humans. And so absence of evidence is no evidence of absence, in my opinion. Yeah, what we know based on the data that we have is that cold sensation seems to drive this perception irrespective of motion on the skin. And of course, tactile modulation is important in modulating the variety of wetness experiences that we have. From a neurophysiological standpoint, that seems to be a central integration mechanisms, leveraging peripheral afferents from A-type nerve fibers, and tryptamate as a molecular transducer, of course, seems to be involved in some ways in these pathways. And then we seem to see some modulations based on sex, with females being generally more cold sensitive and therefore more cold wet sensitive. Same applies to maximal exercise with a temperature-mediated, thermal sensation-mediated reduction in wetness. And with some preliminary evidence that aging seems to reduce sensitivity to wetness from a perceptual standpoint. And so as a take-home message, the way I like to think about this perception, which excites me when it comes to the research about it, is that, this is a synthetic perception. So we can induce the perception, we can suppress it by manipulating the sensory cues that we've identified are involved in these mechanisms, irrespective of the physical moisture. And so in very lay terms, I think Nick has done a great job in showing us how much limited control we have over the production of sweat when it comes to what the actual biophysical requirements are for evaporating, depending on the environments that we're within. And so in a way, from a conscious standpoint, we can't change how much we sweat that much, yet from a perceptual standpoint, we can change how that feels if we manipulate those sensory cues that could be involved in this perception as we've identified them. And so before I conclude, just some acknowledgements. Of course, the lab members and the guys in the lab that do all the hard work, our previous and past and current collaborators, and the funders that support some of this work, and all of you for your attention, and the organizers of the virtual environmental economics. Thanks.
Yes, thank you very much, Davide, for again another excellent presentation showing a nice combination of physiology, neurophysiology, and environmental physiology in one approach, using again smart methodological approaches to study these issues. I'm particularly happy that all three of the presentations made a really comprehensive overview of the topic and really followed on each other. And I think this is really a great thing. We still have time for two quick questions from the audience. In particular, Rochelle has a question which is like usually and generally asked in this type of experimentation and relates to the potential influence of female hormonal fluctuations through the menstrual cycle and its effect on the measures that you did, or if generally you think that there is a menstrual cycle related effect.
That's a great question. That's not something that we've explored in the lab, as it would be a great study to do. Although you could hypothesize that is likely to be a factor. I mean, one thing that we know is that menstrual or fluctuations due to the menstrual cycle, they seem to have an effect on the tactile sensibility of the skin. Often in females that tend to occur in specific body regions, but you could argue that those local changes in tactile sensitivity, given the role of touch in wetness sensing, might translate into differential wetness sensitivities across different phases of the menstrual cycle. So yeah. Yeah.
Okay, thanks a lot. And the next question comes from Nathan Morris, and it's aimed at both Zach and Davide and it deals with essentially given the presented mechanical components of skin wetness perception, does that mean that the mechanoreceptors can influence the thermoregulatory behavior? And with both of your work with the clothing companies, etc., do you think that clothing can have a significant effect on thermoregulatory perceptions and behavior through mechanoreceptors, or changing clothing pressure, etc.? I know it's a broad question, but you can try to answer maybe Davide first and then Zach, if it's okay.
Sure, that's a great question. I mean, some of our results do show that the manipulation of the mechanical cues has an impact on perception. You know, you could also argue that there is some evidence that, you know, changes in skin hydration and the mechanics of the skin, as well as on the saturation of the skin as a result of sweat buildup, has an impact on thermoregulatory responses. You know, I'm thinking of hydromeiosis when it comes to changes in local sweat production. So I would argue that, you know, that there might well be some afference that is involved in there. Yet the thing is, my opinion in this area is that often, due to the lack of you know, studies done in this area, the two areas are often approached in a separate way. The people that do the autonomic stuff and the people that do the behavioral and perceptual stuff. And sometimes if you try to look at them in a combined way, such that you look at the whole thermoregulatory arc, so both the afferent and the efferent, then you start, you know, finding more evidence of potential links between these different components.
Yeah, I agree. And this is the interactions, I think, given the presentations that you made today, this is the next step, you know, to push it a bit further. Zach, would you be willing to comment on the question a bit?
Yeah, of course. I agree with Davide. And I think the short answer is that it's likely. I think the work Davide showed with like the tight fitting clothing versus the loose fitting clothing, and how that modulates wetness perception. The big kind of leap that we don't really know is how that translates into meaningful changes in discomfort, and then how that, you know, and is that meaningful enough to ultimately change the behavioral output. So I think we just don't really know yet, but I think you could easily make educated guesses or hypotheses that would be the case.
Yeah, the interesting thing with that work was that we managed to change wetness perception, but then when we looked at the thermal discomfort of the people, there was no difference between conditions. So you could argue that if they had undergone a behavioral test as a result of that, there would have been any change in behavior because thermal discomfort was the same.
Yeah, and I think to further complicate this, you know, when we manipulated skin wettedness, we did not observe any differences in perceptions of skin wetness. So you know, I think it's too early for me to conclude that perceptions of skin wetness don't matter, but I think it really opens the door to that we really need to try to figure this out.
Yeah, I think that the time is ripe that you two plan the combined experiment, to see
It'll be great.
further develop that.
Absolutely, yes.
Yeah. Well, if there are no other questions, then I think we're just really nice on time, on the planned time. I would like to thank again all the presenters for their great work, and to all the participants, thanks for coming and following the session. Do not forget to follow our internet page and notifications on Twitter. And don't forget that next week we meet at 9 a.m. Standard British time for the Eastern session on firefighting. Yeah? Thanks a lot for coming.